In section 4.3, we're going to look at homogeneous linear equations with constant coefficients. We've already seen several different ways to solve these. In particular, these types of equations are separable, and we also have the idea of solving them with an integrating factor. In this section, we're going to introduce yet another method that will apply to more other types of equations, which is going to be our approach to homogeneous ones that have constant coefficients. If we observe, let's suppose here that we let and assume that we have a solution of the type y equals e raised to some constant times x. Let's take this solution and plug it into the differential equation. Y prime from the chain rule would be m times e raised to the mx power. And when we plug it in, we would get the following. We would get a times m e to the mx plus b times y, which would be e to the mx, would be equal to 0. We have a common term of e to the mx, which we can factor out. That's going to leave us with a plus a times m plus b equals to 0. We know that e is never 0, so we can divide both sides by e, and we get an equation for this unknown constant coefficient for the exponential, which is a plus b, so a times m plus b, which is equal to 0. We can solve this for m, and when we do so, we get the following. We get that m equals negative b over a, so it looks like the function y equals e to the mx, where e is negative b over a times x, should be a solution to this differential equation. And so ultimately, when we supposed a solution of this type, y equals e to the mx, the value for m, that unknown constant, must satisfy this equation where the e part cancels out. This is what's referred to as an auxiliary equation. So this is an auxiliary equation. Let's actually check to see that this works. If y equals e to the negative b over ax, then we would know that y prime would be negative b over a times e to the negative b over a x. That's coming from the chain rule. And if we plug it into our differential equation, we would have a times y prime, that's negative b over a, e to the negative b over a x, plus b times y, which is e to the negative b over a x. This should be equal to 0. Well, these cancel, so we get negative b, e to the negative b over a x, plus b, e to the negative b over a x equals 0. And sure enough, it does cancel out, and we do have a solution here. So one of the things that's going to be nice, we'll see this not only with first order differential equations, but any order differential equation with constant coefficients. This will be a method of solution. We suppose a solution of the type y equals e to the mx. We can plug it into the differential equation. We will arrive at what's called a auxiliary equation, and then we can go ahead and solve that auxiliary equation. Let's now go ahead and take a look at what would happen perhaps if we had a second order linear homogeneous differential equation with constant coefficients. So we have a y double prime plus by prime plus cy equal to 0. We are going to let y equals e to the m of x. Let's suppose that this is a solution, and let's plug that into our differential equation. So y prime, that would be m e to the mx. Y double prime would then give us m squared e to the mx. So we get the following. We have a times m squared e to the mx plus b m times e to the mx plus c times e to the mx equal to 0. And you could factor it out, or I'm just thinking of dividing everything by e to the mx, because we know e to the mx is non-zero. And this is what we get. We get that this coefficient m has to satisfy the following algebraic equation. We need a m squared plus bm plus c equals to 0. And this is just a nice quadratic equation in the variable m. So this is going to be our auxiliary equation. The auxiliary equation, you don't necessarily have to do this substitution every single time. Literally, if you just look at the form of this second order ODE with constant coefficients, you're just kind of swapping out the derivatives for powers of m. So that the second derivative would become an m squared, the first derivative would become m to the first, and if you just had the function itself, be careful. The function itself you can think of as like the zeroth derivative, so you'd have like 0 power of m here, or just a constant. Okay? And then the constants a, b, and c match up a, b, and c. So if we can solve this quadratic equation in the variable m, then that would produce solutions for us. Okay? And it turns out, you might recall this, or you should recall this from algebra, that there's 3 qualitatively different types of solutions to this type of quadratic. We can have either distinct roots, we can have repeated roots, or we can have complex conjugate roots. Okay? Let's go through each of those cases. So in case 1, when we get 2 distinct real roots, then we have 2 different values for m that will work. We get a value m1 and a value m2. So our 2 solutions in that case would be y1 equals e to the m1x plus y2 equals m2x. Now, if m1 and m2 are distinct, then we know that from the Wronskian that these 2 functions will form a linearly independent set, and therefore the general solution would be simply y1 equals c1 e to the m1x plus c2 e to the m2x. Okay. So that's the first case, distinct real roots. This is what we get. The second case is when we have real repeated roots. So what happens if a root is of order 2? In this case, the 2 functions would not be would be the same function, so they would not be linearly independent. Okay? When this is the case, what we can do is our solution is going to look like the following. So we get our first one, which will be m1 of x, but then the second solution will be found by doing e to the m1x. This is from the last section. This is our y1 times that integrating factor we saw before, which was going to be the p divided by y1 squared dx, and that will give us an x e to the m1x. So kind of an easy way to memorize this, if you would, instead of having to use the order reduction like we saw in section 4.2, just simply recall that what you're going to end up getting at the end of the day is going to be your first solution with the e to the m1 of x, but then the second one's going to have a c2x e to the m1 of x, and now these 2 functions then would be linearly independent, and then therefore the general solution would be y equals c1 e to the m1x plus c2x e to the m1x. So with repeated roots, you're going to have 2 exponential terms, but just be aware that the second one's going to have an x with it, and where that's really coming from is by knowing the first solution and then using reduction of order. We didn't show the details here. If you want to see it, just let me know. I can upload a separate video to work through that part of it. But recall, once you have one solution, reduction of order from 4.2 will allow us to find the second linearly independent solution, and so that's where this x is coming from at the end of the day in the general solution here. And then the third case occurs when you have complex conjugate root solutions. So remember that now oftentimes if you're solving these, okay, they're not always going to be nice and factorable like we see here. In general, the real world is messy, and so sometimes the solutions will be 2. But, you know, if you have to, you very well may need to use the quadratic formula when you're trying to solve for m. Recall the quadratic formula is negative b plus or minus the square root of b squared minus 4ac all divided by 2a. It's really good to use this, especially if you're having a hard time factoring, or in essence to where we get either like some funky real number coefficients with radicals, or in the complex case. But in that situation, we want to recall Euler's formula. So technically, when you get complex conjugate roots, so anytime a quadratic has complex roots, they always end up being complex conjugates of each other. And at the very minimum, that means that m1 and m2 will certainly be different. So as we saw in case 1 with distinct roots, it is going to look like y equals c1 e to the m1x plus c2 e to the m2x. But we know that m1 and m2 in the complex case, those two are going to be conjugates of each other. And then to kind of make sense out of this thing, we want to recall Euler's equation, or Euler's formula. Euler's formula says if you take e to a complex power, I want that gone, let's see if I can make it happen. Sorry about that, I'm not sure what's going on with this keyboard. It's kind of crashing here. Anyway, so if you recall Euler's formula, e to the I theta, so e raised to some real number multiple of a complex number I is cosine theta plus I sine theta. If we use that, we can then break apart these solutions and write them in a much more convenient fashion. Also recall that for whenever you have the complex conjugate part, recall the even and odd identities for sine and cosine. Cosine is an even function, so the cosine of negative beta times x is going to be the same thing as the cosine of positive beta x. Here we go. So that's what I was saying before, e to the I theta, that's cosine theta plus I sine theta. In general, if you have this being raised to any complex power, like this, then you can split apart the real coefficient, e to the alpha, and then you would have e to the bi, and then this would be equal to e to the a, which is real, times the cosine of b plus I sine b. So this is what it would look like in general. If you take e to a complex power, you would break it apart. This would be the real part, or a real part of the coefficient. Then you have this e to the bi term. That you can rewrite with Euler's identity, and then we would get e to the a cosine b plus I times e to the a sine b. And so this is our complex number. It's of the form real plus imaginary part times I. So we're able to kind of rewrite this, and I'll let you all kind of work through the algebra, but if you kind of try to simplify this, what you're going to get is going to be the following. The solution in this case would be y equals, it's going to be e raised to the ax, where a is the, where e to the alpha x, where alpha would be the real part of your complex solutions, and then we're going to have times c1 cosine beta of x plus c2 sine beta of x, where beta is the imaginary part of your complex solution. Okay. So just to kind of summarize, here's what we have. If we have our auxiliary equation, ax squared plus bx plus c equals to 0. Case 1 is distinct roots. When we have distinct roots, the solution looks like this. So let's call them m1 and m2 that are different. Then the solution is y equals c1 e to the m1x plus c2 e to the m2x. Case 2 is repeated roots. When we have repeated roots, m1 is equal to m2, and then the solution in that case would be y equals c1e to the m1x plus c2x e to the m2x. And then in case 3, this is where we have complex, well, if it's complex, it has to be conjugate, complex conjugate roots. So m1 would be something like alpha plus beta I. m2 then would be alpha minus beta I. And whenever this happens, the solution looks like this. It's going to be y equals, we get e to the real part of the solution times x times c1 times the cosine of beta x plus c2 times the sine of beta x. So these are the cases that all boils down to. And so in many regards, this is a really nice and kind of easy section, because if you can solve quadratic equations, then you just fit it to the form, and now we're able to solve the second order linear homogeneous differential equations. Okay? The difficulty will come into when we start to do higher order equations like degree 3 and degree 4, and then ultimately it kind of boils down to finding roots and being able to solve some of these auxiliary equations. But for right now, we're going to focus on second order ODEs.